Welcome, chemistry students. Talking about the gas laws here, and I figure I'd start things off with a little chemistry joke here. I just heard this that oxygen actually went on a date with potassium, and it went okay. Come on, you got to think that one's funny. The formula O and K for oxygen and potassium. Anyways, let's talk about these gas laws here. Diving right in, some general rules that you need to know is that temperature must always be in kelvins. And again, remember our conversion of kelvins is you add your Celsius temperature and 273 to that to get it to Kelvin. If more than one pressure is given, they must be in the same units. We can use dimensional analysis to convert. If more than one volume is given, convert to the same unit. Little hint, reminder, 100 or 1,000 mils in 1 liter, and 1 kiloliter is 1,000 liters. 4 things that affect gases in general that you should probably write down: pressure, volume, temperature, and moles of a gas. Now we represent moles of a gas with the symbol N. So that's something that you're going to need to recognize and understand that is representing moles. They're all centered around these 4 factors. Probably a pretty important thing to know these 4 things. Anytime you are told something is STP, we've talked about this before, but very important to note here. I would again star this. STP, standard temperature and pressure, 1 atmosphere and 0 degrees Celsius. Need a little degree sign there. 273 Kelvin. So let's get started on our first gas law. Taking a look here, we have Boyle's law is stating that our volume of a fixed gas, mass of gas, varies inversely with the pressure if we're keeping the temperature constant. So as the volume increases, the pressure decreases. As the volume decreases, the pressure increases. I like to represent this with a volume increases, right? Therefore, remember our 3 little dots that mean therefore, the pressure decreases. And vice versa. If the volume decreases, then the pressure, therefore, the pressure will increase. So it's an inverse relationship. Important factor that you need to know here for the Boyle's law is its equation. So get this written down here. P1V1 equals P2V2. So an initial pressure equals a final pressure. An initial volume equals a final volume. So you're always going to have a situation where it's changing. Now, all these gas laws are about identifying variables. So if you can read a problem, identify variables, you are good to go in being able to do that. And let's dive into our first example problem. We have a helium-filled balloon that contains 125 milliliters of gas. You should recognize milliliters is a measurement of volume. So that's the first volume I'm given, V1, at a pressure of 0.974 atmosphere. So this is going to be my P1. What volume, so that's V2, will the gas occupy at STP? So we're changing this to my second pressure, which is going to be STP. So that's P2 here. So again, I'm all about identifying my variables. So my initial volume is going to be 125 milliliters of gas. The initial pressure is going to be 0.974 ATM. Gotta remember units here, guys. What volume? So that's my unknown. V2 is a question mark. It's going to be in milliliters also because I have initial milliliters given, and it's going to occupy at STP. You have to remember STP, standard temperature and pressure, pressure of 1 atmosphere, 1 ATM. So if you can identify your variables, you're going to have a list of equations to choose from at the time. Right now, we're only given 1 equation, so I'm going to substitute this in. P1 is 0.974 ATM times V1, which is 125 mils, equals P2, which is my 1 atmosphere, 1 ATM, times V2, which is my unknown at this time. Very simple to solve this problem because all I have to do is divide by 1 to get these guys to cancel out. Divide by 1. We know anything divided by 1 is just going to be itself. So 0.974 times 125 equals 121.75. And again, this is going to be, since this is atmospheres here, my atmospheres cancel and I'm left with milliliters. I need to look at my sig figs. For the atmosphere here, we're not going to really worry. STP, usually we go to about 3 sig figs. So I'm going to round this off to 122 milliliters as my V2 for your final answer. And that's our first gas law problem there, Boyle's law. And we talked about how it varies inversely. So his graph here, what it actually looks like is, again, if pressure is high or volume is high, pressure goes down. So it's an inverse relationship, and an inverse relationship graph ends up looking more like this. So this is high pressure, so this is pressure increasing. And up here, obviously, volume is increasing. So at high volumes, it's low pressure. As you move to high pressures, you get a lower volume. So that's our first gas law. So continuing on here, we have Charle's law, which is talking about the volume of a fixed mass of gas at constant pressure varies directly with the Kelvin temperature. And that makes sense here. If we heat something up, we think the pressure is going to go up. So if the temperature decreases, so goes down, then the volume also decreases. So we represent that here as temperature decreases, goes down, therefore volume decreases. It's a direct relationship. And vice versa. If volume increases, therefore temperature increases. You can think of a lot of situations where this happens at. You know, an example here with like a balloon. If it's really cold out and you take a balloon and you stick it in a freezer, you can actually see what happens to it, and it actually gets smaller. And we're going to look here at our Charle's law equation, and we have V1 over T1 equals V2 over T2. Again, our initial and final volumes and temperatures. Looking at an example here, this is our balloon filled with oxygen gas, occupies a volume of 5.5 liters, so that's my initial volume, and 25 degrees Celsius, so that's my initial temperature. What volume, that's V2, will the balloon occupy at 100 degrees Celsius? So this is going way up in temperature, so what do we expect to happen to the balloon? Increase in temperature, I should get an increase in volume. Let's see if it's right. So DI variables here. Initial volume, 5.5 liters. Initial temperature, 25 degrees Celsius. Remember, convert this to Kelvin, plus 273. 5 and 3 is our 8, 9, and a 2. 298 K. Remember, no degree sign with Kelvin. Then our V2 is our unknown volume. It's going to be in liters also because that's what I was given. And my final temperature is 100 degrees Celsius. Again, convert that to Kelvin. 273 plus 100 is going to be 373 K. So my equation, I'm going to substitute that in to my V1, which is 5.5 liters, over T1, which is 298 K, is equivalent to V2, which is unknown at this time, over T2, 373 K. Now to go ahead and solve this, what we can simply do is kind of cross multiply and divide. So I'm going to cross multiply here. I'm going to end up with 298 Kelvin times my V2 is equivalent to, grab your calculator, 5.5 times 373 gives me 2051.5, and this is really liter Kelvin right now. Liters times Kelvin. If you're looking at your units, I need to solve for V2, so I'm going to divide each side by 298 Kelvin. Divide by 298 Kelvin. Again, dividing a Kelvin by a Kelvin leaves me with just liters, which is what I want. So my V2 is going to be 6.88. And I'm going to round that to 6.9 because my 5.5 only has two sig figs, liters. And we predicted at the beginning that your volume would increase, and it did. So the balloon would expand in that example. And that's Charle's law. We said it has a direct relationship between our volume and temperature. So looking at the graph for Charle's law here, volume and temperature is a direct relationship. Therefore, as I increase volume, I increase temperature, direct relationship. And our third law that we have to talk about here is Gay-Lussac's law regarding the pressure and temperature of and it states that the pressure of a fixed mass of gas at constant volume varies directly with Kelvin temperature. So taking a look here at this, it's basically saying as the temperature increases, the pressure increases. So T increases, therefore pressure increases. And the pressure is going to, as temperature decreases, therefore the pressure decreases. Same thing can think here, and a good example of this is like when you're driving your car in the morning. If before you get up on a cold day, you go outside, you can probably push in on the side of the tire a little bit, and it doesn't have that much pressure in the tire. But as you drive it and the tire heats up, the gases again are going to expand because pressure and temperature and volume have a direct relationship. So the gases expand in the tire, and the tire becomes more inflated. The pressure goes up. So in most of the tires, they have those max PSI that you're supposed to inflate your tire to, so it doesn't go over the max pressure, because they're accounting for the tire is going to heat up as it's driven. So the equation looks like this, very similar to what we've seen before here, in that the initial pressure and temperature equals the final pressure and temperature. So let's go ahead and look at an example problem here. A gas cylinder at room temperature, so room temperature here is my T1, is thrown into an incinerator where the temperature reaches 500 degrees Celsius. That's pretty hot, guys. T2. If the gas inside the container was initially at 1 atmosphere, so this is P1, what pressure, so that's my new pressure there, I guess we don't need that second one, did it reach inside the incinerator? Assume constant volume, and it did not explode. So identifying our variables, this is what it's all about. P1, in this case, is 1 atmosphere. T1 is 20 degrees Celsius. Remember, convert that to Kelvin, 273. That's going to equal 393 K. P2 is my unknown, and it's going to be in atmospheres also. And T2 was 500 degrees Celsius. Convert that to Kelvin, 273 is going to be 773 Kelvin. let's substitute these into my equation. The initial pressure was 1 atmosphere over the initial temperature, which is 393 Kelvin, is equivalent to my unknown pressure, P2, over 773 Kelvin. Again, the best way to solve these is most likely to cross multiply and divide. So I'm going to end up here with 393 Kelvin times my P2, and that is equivalent to 773 atmospheres Kelvin, because I'm just multiplying the units together. So I can divide each side by 393 Kelvin, and I'm dividing over here by 393 Kelvin. My kelvins are going to cancel, and I'm going to end up here with P2. My final pressure is 773 divided by 393 equals 1.97 atmospheres, ATM. Again, your units here, what you started with is what you're going to finish with, and that's taking a look at Gay-Lussac's law. Again, we said they have a direct relationship, so the graph of Gay-Lussac's law looks something like this, where down here close to 0 there really is no relationship, so we kind of draw a dashed line, but then again once we get to a high enough pressure and temperature, we have a direct relationship, so it's going to increase just as our Charles law did. And that's really Gay-Lussac's law. The last law that we have to talk about here is our combined gas law. We're going to change colors for this one. So the combined gas law is kind of what it's saying is we're going to take all of these. So the relationship between pressure, volume, and temperature of a fixed amount of gas. And we usually talk about N, or remember, N is moles of gas. So if you're not changing the amount of gas that you have, whether maybe we said you have 10 grams of gas or you have 3 moles of gas, that is staying constant. All of these variables, pressure, temperature, and volume, can be looked at using the combined gas law. And here's your combined gas law. Right here we have P1 V1 over T1 equals P2 V2 over T2. And that's our equation. So let's look at the combined gas law here and this example calculation. The volume of gas at 27 degrees Celsius, so 27 degrees Celsius, that's my T1, and 2 atmospheres. You got to remember, atmospheres is a pressure, so that's P1 is 80 milliliters. We measure milliliters is a measurement of volume, so that's V1. What volume, V2, will the gas occupy at STP? STP is giving you 2 of the other variables, temperature, so that's T2, and pressure, that's P2. So over here, I'm going to set up my initial pressure, P1, was 0.200 atmospheres. My initial volume, V1, was 80 milliliters. And my initial temperature, T1, is 27 degrees Celsius, which we need to remember, convert that to Kelvin. So 27 plus 273 is going to give me my 7, 8, 9, 10. Carry the 1, 300 exactly. That's a nice number for us. 300 Kelvin. My P2 is over here, STP. Remember, at STP, the pressure is 1 atmosphere. The volume is here. What volume? That's my unknown question mark. I'm going to be measuring volume in this case in milliliters. And my temperature, T2, STP. You need to remember the standard temperature is 273 K. So let's substitute this all into my equation, where I'm going to have, there's my equation right here at the top of the screen. So I'm going to use that to substitute in my first pressure, 0.2 atmospheres, times my initial volume of 80 milliliters, divided by the initial temperature, which I found out to be 300 Kelvin, is equivalent to P2, which is 1 atmosphere, times V2, which is my unknown, so I'm going to leave that as a V2 variable, divided by the 273 Kelvin, which is at STP. So taking a look at this, I'm going to solve this out and set it equal to this. So go ahead and grab your calculator. 0.2 times 80 divided by 300, and I get 0.0533 repeating. So 0.0533 repeating is equivalent to 1 divided by 273 is basically just V2 over 273. To go ahead and solve this, I'm going to get 273 from the bottom to the top by multiplying each side by 273. So I need to bring the 273 over. 273 times my answer gives me 14.56. I'm looking for 3 sig figs, so I'm going to round that to 14.6, and I'm measuring V2. So volume in this case, I wrote it right over here in case you forgot, is milliliters for your final volume. So 14.6 there. And those are our gas laws, guys. I know there's a lot to them, but if you can identify variables, we're going to practice that. You'll be right on your way to mastering these gas laws.